Today's session is going to be around real-time forecasting at Lyft. Briefly about me, I'm a technical lead shepherding efforts on forecasting and streaming platform at Lyft. And today's session is around, I'll take the next 25 minutes discussing around how Beam has helped us significantly in our real-time ML initiative. So brief about Lyft. I suppose all of you have heard about it. It's a ride-sharing company, second largest in North America. We operate only in North America. So let's get started. The agenda is I'll just give a brief around providing the context around the real-time ML and forecasting, touch upon streaming platform, the real-time forecasting architecture, learnings, and what's next. So to begin, forecasting is pretty crucial for Lyft, primarily to efficiently manage the marketplace and serve optimal service levels to our riders and drivers. So as you all know, a bitter experience, there's always a negative experience when either you don't get a driver immediately available or you have a high ETA. That always affects Lyft's business. So what we do in forecasting is to ensure we have the best of class forecasting models that can predict rider demand and driver availability. Currently, the real-time forecasting models predict supply and demand in real time every minute. So we operate at all of North America. So there are around 4 million geohash 6s. So we do forecasting every minute on all the 4 million geohash 6. In addition to that, it's all on airports, venues, special events, all that. Every minute we try to forecast for the next 60 minutes in buckets of 5-minute interval. In terms of its significance, it influences a lot of Lyft products, primarily the real-time incentives that we offer to driver and rider, the dynamic pricing, and prime time. So the impact of forecasting is far-reaching in Lyft. So let's get started on the streaming platform. So I just want to take it back to 2021. When we started off our Beam journey, initially we ran a lot of data pipelines, primarily as part of the data platform team, and taking in cases like ETL and CDC. And we're heavy on Flink, but very low on Beam, like three to four Beam jobs. But that's 2021. Come 2024, currently we're on Flink 117, Beam 250, but we see an astronomical rise in number of Beam jobs at Lyft, close to almost 125. We also saw an opportunity in actually going beyond data platform to touch upon product teams like marketplace, security, mapping. So there's a lot of wide variety of use cases that we try to support on using Beam. One such critical one is the real-time forecasting, which I'll be presenting today. So why Beam? To us, it's Flink++. We get all the good parts of Flink. And in addition to that, we get a lot of simpler API from Beam, side inputs, cross-line support, the API abstraction. And also largely it's been the data scientists and all the product team members have been primarily on Python. So they prefer the Beam SDK in Python versus the Java one in Flink. This is a typical deployment workflow. We have open source the Flink Kubernetes operator. We run everything on Kubernetes. So we run Beam jobs as Python processes. And we have this SP_API service, which is orchestrating a lot of our deployments internally at Lyft. So let's get now, I've just given a brief around the streaming platform. Next, we'll just touch upon the short-term real-time forecasting, the architecture, its iterations that we have gone through. Before, I want to just preface it with the scale at which we operate. This is from one job. This is the supply aggregation job, which is trying to build features for supply. It runs as like 7,500 tasks. There's almost 5 million events per minute. And then we have 1 million events per minute for the demand. So it's a pretty complex DAG if you see. A lot of shuffles that happen, pretty complicated. And the volume, the high throughput that we see that influences a lot of our design choices. And Beam has been standing up to that. So our first iterations of our architecture, just I've broken it down to 3 parts. One is the data ingestion layer, then the feature generation, and then the model inference. So events are generated from our microservices on a continuous basis. They get fanned out to Kinesis. And our feature generation, what we did was initially applied all the filtering, enriching, which is trying to convert from lat long to geohashes, feature imputation. A lot of the feature operations were done in one streaming pipeline. And then we do the windowed aggregation style. Typical features you could talk about for the machine learning models are like what are the new sessions in the last 5 minutes? What are the new ride intents? What do we see? What are the states of drivers in which geohashes are they? So all of those form features for our models. These features are written off to Kafka. And then we have this model inference pipeline, which was first of its kind because for long at Lyft, we had microservices for models and then services interacting with the model serving layer. But for the first time, what we did was invoking models through a streaming layer. And the primary reason for this has been the requirement to generate forecast every minute. So what we do is this streaming job collects all the features and then uses defined set of rules to say, hey, when you have all these features lined up to a certain minute, then invoke the model. So a lot of that handling happens within the model inference pipeline. And the forecasts that are generated, like the forecasts that come out of those models, are then written off to Kafka, the feature store, and then offline feature store. This looks like a typical architecture for a feature generation and model inference pipeline, but it came in with a lot of its surprises in our first iteration. Primarily, a lot of out-of-band communications to services for all the feature imputation, enrichment of the data. Also, slowly and steadily, we started increasing the features to be computed not only for 1 minute, 5 minutes, but also last 30 minutes. That caused a severe strain on the streaming pipeline, which, as you know, with the sliding window aggregations, data gets replicated based on your hopping as you slide the window. So that had severe constraints on memory. Also, we saw a lot of metastable failures, primarily relating to long GC pauses and zookeeper leader elections, often causing failures to the pipeline, which almost meant we had to restart the whole pipeline. So those were a lot of challenges on the feature generation side. On the model inferencing side, the challenges we had were the fact that we were writing to multiple sinks. That often, anytime there was a sink that was throttling, we could see the pipeline really stalling, and that eventually led to on-call. So a lot of chaotic experiences with running at that scale. Additionally, there were use cases for teams to actually onboard models in shadow mode. What that means is you run one pipeline in the model in the production mode, and then you want to run it in shadow. In all such instances, we had to again launch another streaming pipeline just to invoke the shadow models for the same input features. This led to a lot of challenges in terms of managing the existing model inference pipeline. So kind of redesigned or re-architected this system. One thing you see is we kind of separated out the data prep, the feature filtering, enrichment, all of that into a different pipeline because this ensured the prep part of the data is taken care of in real time, then written off to Kafka. And subsequently, the aggregations part of it, which is where the heavy lifting happens in streaming, that's all written off to is in a different pipeline. So this kept things more stable from the feature generation perspective because it limited the number of outbound calls we were making. And at times when you see a sudden surge in data, you often have these challenges with trying to make these outbound calls. They all kind of slow down the performance of the job. So at least this separation kind of meant we could scale these systems independently. And one other thing was, as we were computing these feature aggregations, not only were we doing it at 1 minute, last 5 minutes aggregations, as I said, they were also going to 30 minutes. And for all these aggregation, these large window sized based aggregations kind of relied on ClickHouse. What this gave us was an opportunity to serve wider windowed aggregations to models from an offline system, from a different system altogether, and keep the streaming job much more confined to smaller windows because of the fact that the scale at which the pipeline was operating at with 5 million events per minute just meant we had to scale out significantly, and that was a big challenge. In addition, what we did was we also streamlined the syncs that we write, just writing it to Kafka, built a lot of one-off streaming pipelines which consume from Kafka and write it to the different feature stores. This kept it much more leaner, but also helped us scale faster. And this model of approach, the style of end-to-end design, has helped us to go beyond forecasting into other niche teams within Lyft, like real-time supply, pricing. So yeah, this had really a lot of advantages for us. So a few takeaways: decoupling data prep and engineering, feature engineering. I think the other one was choosing the partitioning key wisely. This often can impact your streaming pipeline at large scale aggregations. When you're doing large scale aggregations, filter early, monitor the memory. And then for caching, we relied on the shared objects. That was one thing we didn't do it earlier. So that helps significantly. Next, as we onboarded the forecasting, the models to run in real time, one critical aspect that came into picture was there are periods of times where the streaming pipeline fails, primarily either there's a source or sync failure, if there are transient failures or upstream data changes. That's one case. And the other is when you're onboarding new models. And in these cases, we either had to go with the computation logic that we have built in streaming has to be again replicated in offline also, which wasn't really an ideal solution. So rather than maintaining a separate batch job to as that's a perfect recipe for an online offline skewness issue. So what we did was we went with pure streaming. And the way we did was we relied on internally a source connect P transform, which internally sources both from S3 and Kinesis, S3 and Kafka. We use Flink global watermarks to just ensure there's a source synchronization. That way, at any point in time, we are only consuming from one source rather than consuming from both the sources. So that has helped in bootstrapping and backfilling instances whenever there's a failure in pipeline, because this really plays significantly when you try to onboard new model. You want to compute your features historically rather than running a batch job. We just relied on just running it as a in a Kappa architecture mode where everything gets redone in streaming anymore. Okay, on the learning side, the first and foremost, if you have seen those numbers around the scale at which we grew, 150 pipelines or so in Beam, has been one big contributing factor has been YAML. The previous session was on YAML, so ours wasn't really as sophisticated that is being built in Beam, but it got us to a very good start, primarily because we noticed a lot of feature engineering could just be defined in a YAML config. And that also helped onboard a lot of our users onto Beam because they were largely Python users and they didn't want to learn a new framework in general. So YAML was just the quickest one to onboard onto streaming. So this is a typical YAML file. You have sources, transforms, and then aggregations. So behind the sources and syncs, we kind of abstracted away with Flink connectors and a lot of boilerplate configs, basic scaffolding. All of that was done behind this YAML configuration. And we just left users with defining either newer transforms, which could do the flat map part of it, or aggregations. In terms of tools that we had to build for this, we were exploring Beam.io, but we went ahead with creating a custom pipeline translator. And in this, what it allowed us was to register Flink connectors. So we used all Flink.io, the Kinesis Kafka S3, and the one that you saw earlier, which was the S3 and Kinesis. All these, we kind of rely on Flink's IO connectors, but we just created a very thin layer within Beam to translate, define custom URLs, and then as and when a pipeline is submitted, they all run within Flink, those custom IOs. So that was one big win for us because we have invested a lot on the Flink connector side from Kinesis and Kafka. It also gave us opportunity to explore newer source V2 versions of Kafka Flink. So yeah, that's been a big win for us. Next has been automatically categorizing error logs. Often, if you run Beam jobs at scale, you know when there are errors, you're spooled with a lot of information. And what we wanted to do was to automatically categorize these into user and system based on a certain pattern into the log. And that helps users as they want to look into issues. They get up in the search in our observability stack. So that was a big win. Third was on validation, as this framework touches upon forecasting. And given that it has a significant impact on Lyft, so we want to ensure that every development goes through a proper testing cycle. Typically, staging, we don't get that large amount of data. So what we went ahead was creating like this validation style of pipelines. And with our YAML configuration, what we did was anytime a pipeline was configured as validation, we ensured the sources don't write to the actual exact source, but rather they just do a log. And what this meant was it was as simple as in a YAML, you just say a validation, and then the sinks are not written. You don't write it to the sinks. You just consume it from a source. You do all the exact processing in the job, but then you just don't write it to the sink. Analyze job was another one that, as enabled, allows users to just use this client we have, which is SP, and then you see all the commands. You just type in SP analyze scale. And what we do is we look back into all the metrics that are generated by the job over the last 30 days, and then determine what is the ideal scale for this job. This has helped because we want to take away a lot of manual efforts in tuning the job away from the customer. So this has been a great tool for us. And fault injection tests. This is to, as part of any rollout, we ensure that users can run fault injection tests, both on the SDK processes, the dependencies, all of that. In terms of knobs, what I would say is network buffers, tune that, always have this checkpoint local recovery, just ensures if there is an ephemeral transient error, at least the job can recover from the local checkpoint. Tune the CPU and memory. And if you're running on Flink, one thing I would say is to always ensure you increase the managed memory setting, because by default it's 0. You want to ensure there is memory available for the Python processes also. On the cluster side, we disallow pod eviction. We run it on Kubernetes, so we disallow pod eviction. This is to ensure the streaming pipeline is continuously running. And what this also meant was the downside of this was we saw a lot of fragmentation in our Kubernetes cluster, because the scheduler doesn't really deploy jobs whenever it sees available capacity that's available in different other nodes. So what we did was to seamlessly redeploy multiple jobs on one go. That helped in cost reductions and also avoided this cluster fragmentation that was happening. Okay, it's been a great journey so far and ending onto Beam. But there were a lot of customer surprises throughout the journey. I think primarily because the customers that we were targeting with the real-time ML were people either from a data scientist background or the Swiss who were working primarily on services. So a couple of surprises were around head-of-line blocking. When you consume from Kafka, typically your pipeline, if there's a failure and you try to restart, you start back from your previous checkpoint, which means you're going back in history for use cases like forecasting, where the forecast for now is more important than trying to generate forecast historically, because time has passed. So that was a big surprise for people to educate, and that definitely stands high. The second is auto scaling. There have been very numerous instances where we see a certain spike in demand, could be a Taylor Swift event at a particular venue, and then you suddenly see a huge spike in demand. And all those instances, those regions do get a lot of data, and that kind of severely constrains the streaming job. And then ideally, typically in a microservice, it's easier to add a new pod to your existing service. But in a streaming job, because there is stop the world, restart from a previous checkpoint, it's always been a big challenge. Move on to the next one. I think we've learned in this 3 years of our journey building this platform has been that it has to be easy to use, as we try to touch upon a lot of product teams in the data platform. A lot of tooling that we believed was a priority wasn't the one when we went with product teams. For them, it was more around robust tooling, a lot of observability. While it's critical even on the data platform, we just felt a lot of observability has to be robust enough for them to diagnose errors. Templatize best practices. What we've done is to scaffold a lot of pipeline construction with the YAML. Now it's all about people just using a CLI to just say, I want to create a streaming pipeline with Kafka as an input. and Kafka as an output, we create a streaming pipeline with all the observability all baked in. So that has really helped onboard customers. Our plans, definitely we have seen huge wins with YAML. That has got us to a great start. Where we are heading towards is more on SQL. That's been the next big ask from customers on feature generation. We have seen a lot of success with real-time forecasting, pricing, incentives, and now we want to extend it beyond to multiple other teams. So SQL is one big ask from customers. On the reliability side, yeah, load shedding, this is just more of a turnkey solution we're trying to build on, where at instances where we suddenly see this huge demand, huge spike in load, we want to just try to shut off that load automatically rather than auto scaling or trying to really cause the pipeline to fail because of the sudden spike in volume. The other is the observability into the SDK handlers. I think that's been one of our biggest challenge as we operated at scale on large number of jobs. That's been one of our biggest concern. Okay, with that, I want to end this. And if all of these interest you, if the plans excites you, please do feel free to reach out to me on my LinkedIn or Twitter. We are hiring, so shameless plug. But yeah, if anything this interests you, please do. Thank you.